We're going to go ahead and go over the next part of our interference section, and this is thin films. Basically, if you've ever seen anything like a bubble, like you have a bubble floating around and it has all the rainbow swirl colors in it, or you're at a gas station getting gas and there's like a puddle of water, and inside that puddle of water there's a little bit of gasoline or something floating on it, and inside the gasoline you see all the rainbowy colors in there. That's basically what we're about to talk about, is those kind of rainbowy colors and the bubbles and stuff like that that swirl all around, and then on top of the gasoline on top of water kind of thing. Uh, Thankfully, we're gonna restrict ourselves to a kind of a simple situation. You could expand this to a more complicated situation, but our basic situation is going to be that we have air, oil, and then water. Now this could be more complicated than this. You could have air, oil, air, or air, water, oil, or air, gasoline, water, or something like that. Uh, and we're going to kind of get this result. But we're going to go through with just this situation, keep it simple. And if you ever had to, I think this is the extent of what you need to know it for. But if you ever had to do this for, something went like air, oil, air, or something like that, then you'd be able to work through this and figure it out anyway, based on the arguments we're going to give here. We're going to go ahead and say that the thickness of this film, we're going to label that with a D. And essentially what we're going to have happening is, I'm going to draw these at an angle, but we're essentially doing the version where the light comes straight in perpendicular to the surface, but the picture gets a little complicated, so I'm going to draw it at an angle just so we see. So we're going to have incoming light, whatever light it happens to be. It's going to have some light that's going to reflect off this way, and then of course there's some transmission. It's going to transmit, and then some of it's going to reflect back off here and come out like that. Okay, so that's our basic situation. Incoming light, some reflects, some transmits, and then reflects off the next layer. Now this would be straight in, so that these two would actually be on top of each other, but I'm drawing them side by side just so you can kind of see it, kind of see it happening where these two are next to each other instead of straight in. It does happen at an angle, but it would change some of our numbers. You'd have to know the angle and then know how much it refracts, and it could get a little more complicated than this. So we're doing the simplest case of straight in, straight out. It works at an angle. It's just that it basically means that the oil has to go a longer distance through, or the light has to go a longer distance through the oil and come back out, and so it can kind of change our result, which you'll see in a few minutes when we actually do this. So let's first talk about what happens at these boundaries. So when light is refracted, when it goes through a surface, there's no phase changes. So refraction, T-I-O-N, sorry, refraction means no phase change. But, and you probably figured that was the case anyway, but reflection can have a phase change. And it goes like this. Basically, there's a phase change if you're going from low index, so a low index or low optical density, to high optical density or high index. You're going to get a phase change. Gives a phase change, and it's actually a phase change of, pi. It flips everything over, it gives a phase change. So if we look right here, this is air. Air has the lowest index. In fact, its index in air is about equal to 1. It's like 1.003, but it's pretty close to 1. And we know that this is going to be a lower index than oil. So in the oil, put an O. That's the highest one. Okay, highest. All right, maybe I'll put that in parentheses. This is the high index. This is the low index, and this is somewhere higher than air but lower than oil. Really, just has to be lower than oil for our. This is somewhere in the middle, but lower than oil. And this would be in of water. Basically, whatever's here, we just need this kind of order. NA or N1 is less than N3, or NW in this case is water. The third one, 1, 2, 3, and then the middle one is the highest one. And that's the oil. That's really what we need for our situation here. And so right here, upon this reflection, all crests will reflect as troughs, and all troughs will become crests. And so right here, at that point, right here is a phase change. Phase change upon this reflection right there. Okay? Phase change. But if you look down here, there is, if you're going from high index or high optical density to low index, so if it's reflecting, if it's in a high index and reflecting off a low index, so that's like right here, there's no phase change. The way I think about this is I simply think that going from a low index to a high index, this high index, it's like more rigid for the light. So it's like a nice loose wave coming in from a loose, easy medium, hitting something rigid where it can't really move, and that acts like a fixed boundary. So it's like a fixed boundary, fixed. That's the way I think of that one. And then in this one, it's going from a more rigid two-tier to a less rigid, so this is like a free boundary, okay? And the free boundary doesn't invert. There's no phase change. This one gives an inversion. There is a phase change. It inverts. Okay, so we need to know that first. So that's the first thing you have to remember. So now let's think about, well, what's going to happen? Well, what we want to have happen, or what's going to happen, is that for different thicknesses, this light's going to go in. Oh, I should probably write on here, right here, no phase change in this reflection. So no phase change right there. Okay, so think about this. What's going to happen is this light's going to come in and it's going to reflect. And then this light's going to come through and bounce off the bottom and come back up. And then the reflection off the top surface is going to interfere with the reflection off the bottom surface. And if they are in phase with each other, then it's going to be constructive interference. And so let's say red light came in and bounced off of here and was in phase with itself, then you'd get an amplification of red light. So if the bubble was the thickness here that caused that, where they interfered positively, then you'd see red right there. Okay, oops. You'd see red over here if that's where the thickness was. And if it came through over here, let's say, where the red light came in and it bounced off and it was out of phase, exactly out of phase, totally destructive, you wouldn't see red there. So you'd see red over here where it was a certain thickness and not over here. And then the same thing for different colors. And of course it's going to depend whether or not they're in a phase. It depends on a few things. It depends on what wavelength it is, because you could imagine for certain thickness here that it could be different wavelengths for the different path lengths. It depends on this path length, which is based on the thickness of it. So red light may make, maybe makes a journey where this path length is equal to one wavelength of itself, but blue light, it's equal to like, whatever it is, 1.5 wavelengths or something like that. And then, one would be in phase and one would be out of phase. One would get destroyed, one wouldn't, and you'd get this kind of rainbow effect. So what exactly are the conditions that we need to get this kind of, let's start with destructive interference. We're just going to talk about really just any kind of interference. So let's start with just the regular old index of refraction, so and inside the oil, because we have to worry about a few things like when this comes into oil, the frequency stays the same, but the speed changes, and therefore the wavelength changes. So there's a wavelength in the oil, there's a lambda in the oil, and it's different than the lambda in the air. They're a little different. So we have to worry about this wavelength here for this distance here to decide how much of a path length difference there is. So it's a little more complicated than the diffraction double slit kind of thing with figuring out the path lengths, because we have to worry about what happens to the actual wavelength. So let's take a look at this. So the index of refraction of oil is simply the speed of light in a vacuum over the speed of the light in that oil. Okay? And we can solve this then for velocity in the oil is equal to C over N of oil. Okay? And this is velocity, and velocity equals frequency times wavelength. And there we go. Now we've got our wavelength in the oil right there. Okay? And, that's kind of what we're looking at. So if you look at this, what we've got here is we can do a little quick line. So the frequency stays constant and the speed of light is a constant. So if I rearrange this, divide this f over and multiply this n over, you can get that c over f, whatever the frequency of the electromagnetic wave as the light is equal to the index of refraction of it times its wavelength in that material. And then this is a constant. So that means that N in water times lambda of water is equal to N of oil. So basically this just means that the index of your material times your wavelength is equal to a constant, because that's a constant. So we can set this equal to the index of refraction in a vacuum, which is 1, right, in a vacuum, times the wavelength of our light in a vacuum. Okay? And by doing that, we can basically write then that lambda in the oil, what our actual wavelength is in the oil, or what it would become once it got inside the oil, would simply be the wavelength of it in a vacuum divided by the index of oil. And that's what would happen to the wavelength of it as it entered the oil. And you can kind of think of that. It's pretty close to what it is in air. Not that it really matters what's in air, because we just worry about this phase change, but it matters a little bit, I guess, after this point. But then they all go back to it. But you could measure the wavelength in air. It's pretty close. Again, this is 0.003, I think, if memory serves me. It's something really small. It's very close to 1. So air is very close to a vacuum. Not a very big difference. Now, what we need is for the path length here to be equal to some sort of version, some sort of either for, either whole integer multiple of the wavelength or half integer multiple of the wavelength. And the path is that this light has to go down and back up. So basically, over a distance of 2d, right, we need 2d divided by this wavelength, whatever the wavelength is, has to equal some number of waves. I'm just going to put number of waves. Okay, it's going to be either whole waves or 1.5 waves, or really it could be fractions of waves where, it's kind of a little bit constructive and destructive interference. But we're interested in the whole numbers of waves and the half numbers of waves. And then we're going to talk about whether or not the whole numbers of waves cause destructive or the half numbers cause destructive interference, okay? And then substituting this out, we can get that 2dn, right? We're going to put this in for lambda, is over lambda v. So this is in oil. And then this is in oil, 2d over the wavelength in oil, and this would just be it in the vacuum. Okay, so just its wavelength outside of the oil. And that has to equal some sort of amount or number of waves, whatever that number of waves would be. Now, this then just gives us that 2dn is equal to number of waves times lambda. So number of waves, whatever we're going to call this, times lambda. Now, what do we want this number of waves to be? So for destructive, I'm going to move this up a little bit here so we can see our picture. So for destructive interference, remember, there's a phase change here, okay? And with this phase change, that means all crests became troughs, which means if this goes down an integer number of waves, when it gets back here, like say it entered as a crest, it'll get back here as a crest because it's a whole number of wavelengths that it traveled. But in that case, if a crest enters here, right, so the crest goes in and comes back out as a crest, but the part of that crest that reflects back as a trough. So what we'd have is a crest meeting a trough. And that would be destructive interference. So for destructive interference, we want the number of waves to be a whole number, which means we can do this. We can write 2dn is equal to m times wavelength, where m is 1, 2, 3, some whole number. Okay, and n is our index of refraction of the oil in this case. D is the thickness of the film. so 2D, a D down and a D back up. M is some integer multiple of the wavelength, so we're getting whole ones, and then lambda, of course, is the wavelength in a vacuum, and that's our criteria for destructive interference. Okay, so that's our first equation right there. Now, what would it be for constructive? For constructive, we want the opposite to happen. So for constructive, our crests become a trough here, and what we want this crest to do is go down here and come back up with some half integer multiple of the wavelength, so that when our crest gets down here and bounces back up, it's at the phase where it's now a trough. And what we'd have is a trough and a trough meeting. We had crest go in, trough reflects, and by the time that crest gets back up here, it's become a trough as it goes, goes up and down and up and down, and it vibrates through, and we get this whole half integer thing. So what we need to do with this is something very similar. We need 2dn, and we need this equal to m plus 1/2. So this is our number of waves. We need some integer, this could be 0, so it'd be half a wavelength, or it could be 1.5, 2.5, 3.5, 4.5, so on and so forth like that, times the wavelength. Like here we can have m equal to 0, 1, 2, 3, so on and so forth. Okay, and this is our second equation. This one's for constructive interference in this situation. Now, you have to, I think this is the extent of what you need it for this course. But if you are asked about something where something else happens, like say for example, this was air, oil, and then we had something like maybe a sheet of diamond here that had a higher index. So in other words, what if this had the highest index, if it went from low index to mid to high? Well, we'd have a phase change here, but now we'd also have a phase change here, which means these two equations would flip-flop, because this would phase change, the crest would become a trough, but then down here it would do the same thing. So the constructive interference equation would become the destructive, and the destructive would become the constructive. And conversely, if we had this coming from high index to low index, and so we had a no phase change here, and then we also had no phase change here, then these two equations would flip-flop. Okay, so you have to pay attention to how many phase changes there are. If there's one phase change, either here or there, you're going to get these two equations like this. If there's two phase changes or no phase changes, then these two are going to flip-flop. I think you only really need to know it for this situation of the oil on top of water, so this is all you need to know. But if you are asked to think your way through a more complicated one, you got to pay attention to how many phase changes there are, because basically a phase change is equivalent to a half a wavelength of path length difference. Okay, it flips everything by half a wavelength, and that means the constructive ones are the ones that are off by half a wavelength, and the destructives are the whole wavelength ones. Whereas in the the converse idea, if there is no phase change, then the constructive ones are the ones that are off by whole wavelength, and these are the half wavelength ones. Okay, so it's a little flip-flop because of that phase change. All right, that is pretty much it.